If you schedule a time that you said that you're going to interview and you don't show up, it's a 0. You cannot reschedule to something else. There's only one spot available. So if you haven't scheduled, that's one yours. I had a couple of spots today nobody used. My schedule is full. Between all my classes, I don't have any other time. So if you miss it, you miss it. It's 30 points that you're gonna lose. All right. So I know that one student didn't show up. Gonna get 0. All right. So make sure you know your time. Do you have, yes.
Could you talk a little bit about going to the interview and what you back and, be prepared for?
So homework, very obvious. You have a problem to solve and there is a bunch of deliverables, right? Make sure the type of file I requested is correct. You have done MATLAB. I always require M file, the report published. I asked you to justify your answer. So one paragraph, what did you do? Why did you do it? And then for the interview is like, I ask you why you did this. You should be able to answer that since you did the project. I'm not gonna ask you something outside of this homework. So the steps that you did to get here, I will ask you a question about those. Things that you should look. So when you're writing your report, it's good to have the step info stuff there because that's what you use to design your controller. If you don't have it, you didn't give me all the information, right? So nothing more complex than if you submitted a homework. It just has interview because I think at some point when you do things on your own, I don't know if you understood what you did, why you did what you did. So this gives me an opportunity to see like if you understand why you're doing this. Okay, that's the part that you will remember hopefully from the scores, not just on the paper. This thing makes sense. Why did I do that? All right. So those of you that it's 15 minutes. So how many questions I can ask, right? So prepare for 15 minutes of questions. Yes.
Stupid question. How do you schedule an interview?
It's not as stupid, but it's late. Okay.
You found the one.
Literally. Go to your calendar and then here, make sure you chose the control. Here you are in the right week. Yours should look like something like that, like it's slightly different from mine. And then you see that today I had so many available and then there's only one 9:15 on Monday. That's not reserved. So take it, yeah, because PC only, okay. It was part of your last week's assignment to do this. So, yeah. Because a lot of time you do things on the paper, you have 1 week or so, and then you come to the exam like, oh my God, what is this question? Like if you understand what you did in your homework, you should be able to answer all of those in your exam, for example. So this interview is just like that, like live quiz of what you just did. And so if it is your work, you know what you did, you're able to answer. If it's not your work, but you understand it, so I give you the benefit of the doubt and it's like, okay, you understood. Does that make sense? So I'm not going to look for if you cheated or not. If you understood what you sent it to me. Okay, that's a goal. All right. So I re-uploaded. Why did this not show? Huh. I shared it. The screen share what? So I changed the lecture slides. I uploaded a new one. So if you printed it in the morning, there's one slide that I added, this one. This is just extra because I already talked about it in previous lecture, but I put a picture, like a more detailed explanation here. So to help you understand. Also, we are in chapter 8 of your book. I think in last class I said chapter 7, last lecture, we are chapter 8. Chapter 7 is root locus. So we talked about non-minimum phase system and minimum phase system. I forgot what was the name. And this is when we have zeros on the if all zeros are on the left-hand side, we're not talking about poles. If all of the zeros of the system are also on the left-hand side, we call the transfer function minimum phase. But if we have, let's say, 1 0 that's on the right-hand side, is not going to do anything with the stability of the system. It's going to impact the phase, right? So here's an example. If you look at these two transfer functions, they have similar gain, similar poles, right? Different zeros. So if you plot Bode plot for both of them, you'll see that for magnitude plot, they're both on top of each other. So that orange has the blue underneath it. So it does not impact the magnitude. We didn't expect it. But for the phase plot, you see that there are two different ones. So one is minimum phase, the other one is non-minimum phase. So this is G1 with the 0 on the left-hand side, and this is G2 with the 0 on the right-hand side. You see there is a phase difference between them, right? Now this is if you had 1 0. Now if you have 2 or 3 zeros on the right-hand side, this difference will be larger, okay? So when we are designing a controller, we're also looking at phase, right? So you want to pay attention to look at the 0 just for this reason, not for stability, okay? Sounds good? So I wrote it in the last lecture, just one sentence, but now you have the whole thing here if you wanted to use. All right, so this is left from last lecture. I'm going to go over before I start what I had for today. So most of the system in the nature around us act like low pass filters, okay? So you have some gain and then something is filtered. It has a little bit of peak, so it will tell you it's a second order system, right? And then you go down. Most systems, when we model them, are second order system, right? Second order, third order system. Like third order, if you have a controller, and second order, you are changing the whole system. But so if your system is behaving like this, we can conclude a few things from the behavior of the system. So if you remember, damping coefficient is really important, right? To discuss the system properties. Now, if we plot the, when we say complex pole, our system is second order, right? If we plot for different values of zeta, so if you change the zeta value, so your poles are changing, right? So you have two poles. You remember that if zeta is less than 1, you have underdamped system, right? If zeta is 1 and zeta is greater than 1. So all of those also apply in Bode plot, but the way that they look is as such. So this here, zeta equal to 1, this is your zeta equal to 1, right? And critically damped system. And if you have zeta above 1, you have overdamped, and then if it is less than 1, you have underdamped system. Now you see that as you decrease your zeta, you can have an overshoot, you can have a peak in your system. All right. Now, when zeta is 0, what does it mean? Okay, on the axis, right? Imaginary axis. What does it mean physically? No damping. So this is the same thing. So when you don't have any damping in your system, you expect to have that peak, right? Now, who asked the question about Colin? So resonant frequency. So when you are at this peak, so this peak, whatever it is, the resonance, the frequency that you reach the peak is your resonant frequency. Now, what is natural frequency of a system? Let's put this aside. What's the natural frequency of the system? Where do you get it from, let's say? So you get from transfer function, remember? Omega n squared over s squared plus 2 zeta omega n plus omega n squared. So you can find the natural frequency of the system from system. It's a system characteristic, all right? Now, when you don't have any damping, so your system is oscillating, right? If it keeps oscillating, and let's say it's unbounded, the frequency is gonna, so this peak frequency is called resonant. If this resonant frequency is equal to your natural frequency, what happens? bad things happens, right? Goes under control. The system becomes unstable, unboundedly. Now, it can have different implication. Like if you have a glass that has a natural frequency, if you can hit with a force that the frequency of that is equal to your natural frequency, is going to shatter right there, like into little pieces, right? So right now, if we have unforced, just the response of the system, the peak is the resonance. Now, if you apply a force that moves that to a specific value that's equal to your natural frequency, then bad things happen. Now, bad things depend on the system or different things, right? So for the glass, it's going to shatter. If you have something that's oscillating like, I don't know, like a pendulum, it's just going to keep going back and forth and goes unbounded, right? So different implication depending on what is the system, but the system goes unboundedly will be unstable. So something bad will happen. Now, for us, it is important to know what this peak is. So just be careful. This plot that I'm showing here is not exactly the body plot. These are normalized. So omega, all frequencies are divided by natural frequency. Okay. It means that when we have omega over omega n equal to 1, means that the frequency of the system now is equal to natural frequency. If that peak happens, then the bad thing happens. All right. Is at that a point of no damping. Because if there was damping, we wouldn't get there. All right. Now, so when zeta is 0.7, this is when we care about the system. Like we want to look at the system when zeta is around 0.7, right? Remember? So you want to read the value of your frequency for that. Now, your omega n will be equal to bandwidth. We define it the other way around. We said at negative 3 dB, wherever frequency is that is our cutoff frequency, and all the frequency to that cutoff frequency is called bandwidth. So for zeta equal to 0.7, we are gonna say that our bandwidth is equal to our natural frequency. It's very close to it. Why do we say that? Why are we going to use that? Do you remember when we were in time domain, we calculated rise time using our omega n, 1.8 over omega n. It's not exact, but it's a good approximation. So you could say here as well, omega bandwidth, PR. We saw this in the last class, right? Omega bandwidth. So if we needed to see how fast the system responds, we need to look at rise time, right? So if we know the bandwidth of the system, we can tell how fast the system is responding. All right, so we're trying to connect those specifications to body plot. So how system responds is really important. And then from body plot, we also care about PM, the phase shift, right? Because as control engineers, sometimes we like to decide about how much output and input can be out of phase, how much phase margin we can have in our system before the system goes unstable. So these are the two things that you want to look at when you are designing based on a body plot. Means when you're designing based on frequency requirements. Okay. So these are systems that look like low pass filter, right? Now, if you have complex zero, so for pole, you see that the slope is -1. So for zero, just the slope is positive. But if you have a complex zero in your system, so this wouldn't be set with just a transfer function that you have complex zero in it. But you can add them together. So if you have zero pole, the combination of them becomes your body plot. So for a system that has zero and pole. If you create a system that has zero and pole and plot the body plot, you can see the distinction where it is because of the zero and where it's because of the pole. Now, We talked about the response of the system, how fast the system responds. We should look at bandwidth, right? We also are usually very interested in a steady state error, right? So from time domain response is very easy. You look at the time response and find the steady state error. For body plot is a little bit different. It's not very like obviously clear, but you can find those error constant that we calculated before, Ka, Kv, and Kp from your body plot. Now, if I have a body plot that looks like this, this is like a low pass filter, right? Let's say. So this is the exact body plot. Here is the asymptote. All right. So finding Kp, Kv, Ka from body plot, we need to look at the asymptote. So if the system is type 0, the low frequency asymptote is constant, is a flat line, right? For type 0 when you don't have any integrator in the system. And your open loop system gain is your Kp. How do you find open loop gain from body plot? You find your max gain. Then if you have system type 1, the low frequency asymptote has a slope of -1 or -20 dB. The one I showed right there. So that is a type 1 system. This is -1 or 20 dB. Now, if I want to find Kv, you can find here on the omega on frequency, read wherever omega equal 1 is and go to the asymptote, not to the plot, to the asymptote, and go read whatever gain, let's say in dB, you find, that becomes your Kv value. Now, if you find it in dB, you have to convert it to volt per volt, right? To make sense. So that becomes your gain for error constant for system type 1. For system type 2, the slope is just -2. You do the same thing, but the slope is different. Like there's a sharper system. It would be like that. So this is your body plot, and then you go read this number. All right. So this is if you want to find the error constant from this. Usually, one of the requirements is that we need to have 5% steady state error for the system design control. You need to know what gain will be that 20%, right? So you calculate 20%. Oh, this is system type 1. I need to have a Kv. I'm going to go find Kv from there, and then this becomes the K of your system. Now, if you have system type 2, same thing, but it's just Ka. Now, if you remember from system type lecture, Kv was limit of SGS, right? Ka was limit of S squared GS. Same thing. So you put the value you have, steady state, 1 over Kv. So if it's listed as 2%, so 0.2, 1 over Kv, Kv has to be 20. Then put in the equation and you find the Kv value, right? So that would be the way that you will find K. Don't worry, I put a few examples, I think one big example that can help you how we do that. But these are two different things. One from the body plot, just by looking at it, one by doing it, calculating it mathematically. They should give you a good, again, educated guess to start. Then you have to look at your response and see if it meets your requirement. It does not always give you the exact value. Okay, so we are in control of design. Everything has to be changed. But the good educated guess if we go from there. So these were left from last class. Now, here's an example. Hopefully it will help a little bit to clear things up. You have a system. This is the open loop system. What does it mean? This is just a transfer function of the plant, right? GS. K is if you wanted to have a gain plot before your system, that would be your KG. Now you know that because it's in this form, you could use this to plot your locus and stuff. It looks like the standard form of the locus, right? So questions are, what's the system type? what value of K will give you a PM greater than 30 degrees, maximum possible closed loop bandwidth, and the steady state error for the chosen K using body plot, the graphical part that we just talked about. All right. Now, what is system type? By show of hand, raise your hand, use your finger. Type 2, because this is 2, so system type 2. Now, what value of K will give us PM greater than 30 degrees? Now, basically asking us, like, if K was your controller, right? For what value of that controller you would give a phase margin of greater than 30? If you remember, as design engineers, we want to always stay to the minimum of 30 degrees, right? So we are trying to find the minimum value for K. That's basically what we're starting with asking. Now, what would you do? What do you think we should, where do you think we should start? G is your system. Like, it's like,
Or the gain.
so if the gain is 0, what happens to the system? So 0 divided by some number is 0. Again, same thing. The system, you just poof the system. So 0 is not, you're going toward the right direction, but 0 is not the right number. Okay. At 1, because it's just the system, right? So 1 times the system is the system. So now what, so we choose K as 1 because we want to know what does the system look like without being compensated at all, right? Because K equal to 1 is also like you haven't done anything. Now, what do we look at? What are we going to do now? So we can look at the body plot. Why do we want to look at the body plot? Because we have phase margin, right? So you have a bunch of choices. Look at the step response, look at the root locus, or look at body plot. We want to definitely look at the body plot because we have a requirement of phase margin. Okay, so we are going to plot the body plot for an uncompensated system, K equal to 1, right? Let's do that. Here for K equal to 1, this is our system. Now, what is the gain and phase margin? So we are going to design for phase margin, right? What's your phase margin? Nelson. 4.5 degrees, and it gives you the crossover frequency as well. It's pretty cool. You don't have to find anything. So, what did you want to do? What was the requirement? Above 30. Right now we have 4, right? We need to fix this somehow. How do we fix this? What do you think? What should happen? Think about how do we find phase margin. Now, from there, what should we do? I'm going to help you with where do we find phase margin. We go to 0 dB, crossover frequency, this is 0.1 radian, which is here. And then, boom, phase margin, which is little, 4.8. Where did we want the phase margin to be? Let's say this is negative 150. So there's 30 between 180 and 150, right? So we wanted this. So for that to be phase margin, what should happen? You read phase margin at. So you have to literally grab this magnitude up. So this 0, if this is your 0 dB, happens here. So it means that you have to shift this much up. Does that make sense? So when you shift it up, now your 0 dB happens at different frequency. Then you go read, and it was the frequency of negative 150. So you have at least 30 degree phase margin. I want you to review this in your head for a minute and understand what happened. This is like literally the whole design.
Why did you go to negative 150?
So we needed PM, our phase margin, to be greater than 30, right? So we go for 30. How do we calculate phase margin? So if you remember P1 negative 180, this has to be 30 to solve that. So it's 150, right? So 150 is our bare minimum, right? So anything above that will be fine, but you want to find that. So how do we grab this thing to go up the magnitude plot? Different case, right? Do we know what case? No, we just need to draw for buffer, right? It's tuning a controller, there is no right answer. You just draw for bunch of them. So we'll draw for different values of K and see which one crosses that point. It doesn't have to be the exact at negative 150 is greater than negative greater than 30, right? So if you have it slightly above, you're fine. As long as we keep plotting the margin of our system, it gives us the number, so you can just check. Now, so that's one way. I will show you the solution in the next slide, but I'm going to go back. So that is it. We plot for different values of K. We will find in what region we will find a K, eventually. Now, what was the other question? So we answered this question. The maximum possible closed loop bandwidth. How do we find this? The bandwidth happens where? Negative 3 dB, right? Yes? Yes? You're not sure. Yes? So, how do we find maximum bandwidth? What does that imply? What does that mean, finding maximum bandwidth? Well, we know bandwidth happens in negative 3 dB, right? We just plotted for a different value of K, we're gonna find a 3 dB of that. Is that gonna be our maximum?
No, it's not. That's the only-
Okay, let's say when you do the Bode plot, so we can look at the open loop system and it'll tell us for the Bode. Okay, when you put K, what does it mean? You're designing a controller, right? So that's cool. For different values, if you are looking at the so this Bode plot is open loop, but by looking at that with the controller, it gives an idea about the code. Now, how far can I change K? How far can I increase K? Anybody has any idea? Or just go home. Let's talk about this. Thank you. Gain margin is where you will be limited for increasing your gain, right? Because eventually you're going to run out of margin. Okay. So we have a gain margin of what? So GM is 64.1 dB, right? So this means that if I have a gain of this much, I'm going to come unstable, right? Or margin stable. Now, this is in dB. Can I use it for gain? Or system like K equal to 4? You have to convert it, right? To volt per volt. We have the equation, right? So if you remember from probably last week, 20 log of M is dB, correct? So M is 10 to the power of dB, which is 64.1. So your M is something around 1598 or 1600. It's like very close to that number. Okay. So this is our gain. That, what happens at this gain, if this was our gain, what would happen? At 0 dB, we will get 0 phase. And anything beyond that, the system is unstable. right? Because this was margin. That's what gain margin means. So the K that you can apply to the system can be up to this number. Now, if I have this K and I plot my body plot and I find that bandwidth, that's the maximum bandwidth I can. Because after that, the system is unstable. Make sense? All right. So we find then, so this is M. So this K is 1598. We plot, body plot, and then we read the frequency we read the dB, the magnitude, read the frequency at negative 3 dB, and then that's our bandwidth frequency, right? So here are basically the plot of both of them. I showed them together. So plotting for different values, okay? So you have system, and you can say case 1, 50 times system. So those numbers you see are very random, right? You choose. So you can say 50, 100, 200, 500, 1,000, 1,500. You are very particular person. You just like pick random number you tend to do. That's your first iteration. Then you find your range, right? Same thing that we use for low pass filter design. That's the same idea. So this is parametric tree. We're using a parameter that you're changing to find the solution. So you find a number that's close. So let's say K equal to 50 would be the solution to our first question, which was PM30. So PM30. So here is phase. Let's say this is negative 150. Let's say it's this one. So this is the orange one. So let's say for K equal to 50, PM greater than 30 or equal to 30 for any K greater than 50. So it would be more correct. Okay, so that's the first part. Now for the bandwidth, we found 1598. So let's say that's 16. So somewhere between that and that. So close to this 1660. So negative 3 dB line, and then let's say, because all of these are very close. So negative dB line, this, we read this frequency, this becomes our bandwidth. So meaning that max bandwidth at K equal to 1598 or 1600, whatever you want. Yes.
At that max, and what's the base market?
There are two different questions though. So one was, so it's not and. There are different cases for the system, right? You can be at negative at 30 degree phase margin and maximum bandwidth. But thank you, I should explain. Those are different cases that you could face in the system. One, hey, we have a phase margin requirement. How do you go about that? The other thing is, for every system you deal with, what is the maximum bandwidth? That will give you an idea of how much you can increase your K value, right? So we found that one as well. Now, let's say the system has some steady state error. It's the third type of question that you can answer using that. So, what was system type? Type 1, right? Type 2, sorry. System type 2. We need to find Ka. So ESS is 1 over Ka. Ka is limit of S squared G of S. S squared cancels out with the S squared denominator. So that's the way that we calculate. But from the body plot, for the K that you want, whatever is the K of your system, whatever a body plot that you plotted, read the dB, read your magnitude. I'm going to read magnitude because then you need to convert it to K, word per word. Magnitude at omega 1 radian per second. This will be close enough to your Ka, so it will be a good number that your steady state error, you can calculate it based on that. So yes says it's 1/KA, you can find KA from there, and then that would be your steady state error. Now, let's say you have a steady state error value, let's say 2%, right? And then you want to know, does your system generate that KA? You find KA, you go on both plot, that's the DB, that's the magnitude. You go across the magnitude plot, go down with the frequency, right? And then from there, see if that moves the other point. If it needs to be shifted up. All right, so all of these three cases are the kind of question that you could come across or answer, kind of question you can answer using Bode plot. So Bode plot doesn't show all the system specification, but the important ones you can tell. Price time from bandwidth. You can tell us about the steady state error. You can tell about phase plot, the phase that is really important in the design. In frequency, right? Any questions? No? Yes, be careful. If you're reading from dB plot, you have to convert it to volt per volt. But shouldn't be a problem. You can just write a code, right? 10 to the power. All right. So what time is it? Ooh, we're almost out of time. All right. So far, the kind of controller that we design, we use in different domains, you can design different controllers, right? You can design, we talked about lead and lag compensators. You could design them in frequency domain as well. Actually, designing lead and lag in frequency domain makes more sense. So, lead controller acts like a PD controller. Lag controller acts like a PI controller. So, all the specification that you have in PD and PI applies to lead and lag. But the more powerful thing is that you could use lead controller when you have PM requirement, phase margin. If your system has to have a specific phase margin, or your output has to be shifted with a specific amount of phase from your input, you can design a lead controller. Okay? It's like a PD controller, it doesn't matter. Like, they will look kind of the same, but the pole and zero that you put in. All right. Now, if you just plot the Bode plot of the lead and lag, you're gonna get something like this. So the lead compensator. So you see that there are two kind of cutoff frequencies. So this is not called in cutoff frequency; it's called in breakaway frequency. So if this was the asymptote of the low frequency, and this is the asymptote of high frequency, you have these two frequencies. So omega 1 and omega 2. These are the pole and zeros, the frequency of pole and zero that you put in the system. Do you remember what was the lead controller, lead compensator? How did you create one? Yes, domain. It's the same thing, same controller. You just like use two different domains. How do you remember?
Adding a pole.
And
It's zero.
so adding a pole and a pair of zero. So both lead and lag are adding pole and zero, but one of them, the pole is closer to the matching axis, the other one, the zero is closer to the matching axis, right? And they both look like S plus Z or S plus P. So we're replacing the pole and zero, find regular values. Now, if you think about, again, S is J omega, right? So if we know what frequency is that, it's the same thing. You're designing the same idea. Now, when you are in frequency domain and you know that there are two frequencies of interest, temperature, if you want this Bode plot to cross from those, if you can find those frequencies, you can design your controller from there. So it's like kind of reverse engineering. I want it to look like this. Now let's design control. Right? For lead control, for that lead compensator, so a lower frequency does not change the magnitude of your system. On high frequency, it does. The good means also you want to get rid of some noise. lag compensator, and just shift it the other way around. Just because our pole and zero location are different, so omega 1, omega 2 are just, all right? Okay, we are gonna stop here, because if I start this, it will take more than 5 minutes, but on Friday, we're gonna do some, finish up the design example we had from last week. So you are supposed to review those design examples. I'm gonna just go over them. So the design example from last class was root locus, remember? So it was root locus, you had system requirement omega and zeta. You can create the area that is acceptable, place your pole and zero. Review those before Friday, you can stay home, we're gonna finish that. And then next week, the last week of classes. So I thought I would finish this today, I didn't. I'm just gonna show you what is left. So basically what our lead and lag control, how to design them. Then I put a design example here. This is for you to go over yourself. It's step by step how to do this. Like I literally did it and then wrote step by step what to do. I'm not gonna go over this one, but I'm gonna finish up the lag compensation because at least like how it is formed, and this should help you to be able to do the project. All right. And last week of classes, we're just gonna hopefully get to state space control. I want to at least touch this on that. All right. See you on, I'll see someone tomorrow. What? I will be here as usual, but